Have you ever typed a question into an AI and just stopped and wondered what's actually happening in there? You know, how does this machine, this collection of circuits and code, make any sense of our words? Well, I promise you it's not magic, and we're about to pull back the curtain on the entire process.
It is a fantastic question, and the answer isn't just one single thing. It's a journey. It's a whole step-by-step adventure that every single sentence you feed into an AI has to take to be understood. So, in this explainer, that's exactly what we're going to do. We're going to follow one simple sentence, kind of like it's our main character, and trace its path from plain old English all the way to a final meaningful answer from the machine.
Okay, let's meet our hero, a single sentence. Its mission, should it choose to accept it, is to be processed and truly understood by a powerful language model. But before it can get to the AI's core, it has a few really crucial stops to make. This right here is the roadmap for its entire journey. Every single piece of text, whether it's one word or a whole book, follows these 4 fundamental steps. So let's dive into that very first one, the translation.
So, the very first challenge our sentence faces is a language barrier. I mean, computers don't speak English, they speak in numbers, so our sentence needs a translator. And that, my friends, is where tokenization comes in.
Tokenization is basically the act of chopping up a sentence into smaller pieces. We call them tokens, which can be words or even parts of words. And then each of those little pieces gets swapped for a unique ID number from this massive predefined dictionary. And here you can see that transformation in action. On the left, we've got simple text that you and I can read. But on the right, that's what the machine sees, a nice, clean sequence of numbers. After this step, our sentence is finally speaking the computer's language. So, how does this actually happen when you're coding? Well, modern AI libraries make this incredibly simple. There's basically one main, powerful command that handles almost any text you can throw it at, making this whole complicated translation process feel almost effortless. Of course, it's not always that simple, right? What happens if the AI runs into a word it's never seen before, like a new company name? Or how does it handle a whole batch of sentences where some are really short and others are super long? And the solutions to these problems are actually pretty clever. For those unknown words, the AI uses something called subword tokenization to break them down into smaller, known pieces. To handle different lengths when you process a bunch of sentences at once, it uses padding to make them all uniform. And this is key. It also creates an attention mask, which is just a guide that tells the model exactly which numbers are real words and which ones are just filler that it should ignore. All right, our sentence, which is now a clean sequence of numbers, has made it past the first gate. It's ready to enter the core of the AI, the transformer model itself. This is where the really deep thinking happens. Now, to get inside, developers use this wonderfully convenient tool. You can think of it like a master key for all the different AI models. You just tell it which saved model or checkpoint you want to use, and it automatically figures out and builds the exact right structure needed. It just removes all the guesswork. It's awesome. So inside, the model performs literally millions of calculations, analyzing all the relationships between every single number. But what comes out on the other side isn't a simple answer. No, it's something much richer, a high-dimensional tensor. Just think of a tensor as a really sophisticated container for data, kind of like a spreadsheet but with multiple layers. It's packed with rich, contextual info about every single word. And for our model here, this data container has exactly 3 dimensions. But what could a 3-dimensional object made of numbers possibly represent, right? Well, it turns out each dimension has a very specific and very important job. So here's the breakdown. The first one is batch size. That's just how many sentences we're processing at the same time. The second is sequence length. Pretty straightforward, it's the number of tokens in each sentence. And the third, hidden size, that's where the real magic is. It's a dense list of numbers, a vector, that captures the deep contextual meaning of every single token based on all the other tokens around it. We've made it to the final stage of the journey. The model has done its deep thinking, and it's given us this complex tensor. Now we need to translate this abstract stuff back into something a human can actually use. These raw scores coming out of the model have a special name. They're called logits. And here is a super important thing to remember. These are not probabilities yet. Think of them more like raw confidence scores. A higher number is better, but they don't add up to 100%, so they still need one more step. To make sense of these logits, we need one more piece, a model head. This is an extra layer that gets bolted onto the end of the main model. Its only job is to take all that rich, contextual information and boil it down to answer a specific question, like, hey, is this sentence positive or negative? So we have our task-specific logits. The very last step is to convert these scores into something intuitive, like probabilities that add up to 100%. And for that, we use a handy mathematical function called softmax. And just look at that transformation. Softmax takes those raw, kind of hard-to-interpret logits on the left and turns them into the clear, intuitive probabilities on the right. Now we can see with total certainty the model is 80% confident in the second option. The verdict is in. And that's it. That is the entire journey, from start to finish. Let's just do a super quick final review, shall we? First, the tokenizer translated our words into numbers. Then, those numbers went into the core transformer model, which analyzed them to produce raw scores, or logits. And finally, a special model head and that softmax function converted those scores into a clear, understandable prediction. So, from a simple string of text to a confident prediction, that's the journey. It's the same pipeline that can summarize articles, translate languages, or even write poetry. Now that you understand how it all works, the real question is, what linguistic puzzle are you going to solve with it next?